We at Yonder Dynamics are excited to present Contingency, our rover for URC 2025. Yonder Dynamics is a student-run project team from UC San Diego, and our rover has proven to be robust and capable across all 4 URC missions. For delivery and equipment servicing, our aluminum frame drivetrain utilizes a rocker bogie suspension that is light and robust. It easily tackles difficult terrain with its differential bar linkage for the delivery mission. Our velocity-controlled drivetrain motors deliver consistent power with feedback, allowing our drivers to confidently control our drivetrain across all manners of rough terrain during missions. Our rover electronics are consolidated in an easy-to-access main enclosure within the chassis frame.
With custom PCBs that manage power distribution, controls, and communications of the arm, drivetrain, and science modules, our electronics help keep the rover compact, lightweight, and functional. With our compact driver station, we have an accessible long-range broadcast station which allows for quick and easy setup before missions. From this driver station, our rover can operate and communicate up to 1 kilometer away from the main driver station. With a 5.8 GHz high bandwidth communication system, we can transmit multiple high-quality, low-latency video streams simultaneously, giving drivers a clear understanding of their surroundings to accomplish their mission. With a website-based front end, coordinates are input for navigation and drivers can monitor the rover's position and path during the entire mission.
Our current 5 degree of freedom arm utilizes a closed-loop joint-by-joint control law to perform equipment servicing tasks such as manipulating switches and buttons, opening door handles and lifting 5 kilogram weights, and plugging in USB drives. Our user-friendly front end provides multiple camera streams and an arm visualization, giving drivers full awareness of the arm's position at all times. Since the 2024 URC, we have been iterating and improving upon a new 5 degree of freedom arm to further elevate our equipment servicing performance. With overhauled position-controlled brushless motors, torque-dense harmonic drives, and a reduced backlash belt and chain system, this new arm can operate with excellent precision and dexterity. And our enhanced camera vision and arm controller makes driver training seamless and efficient.
Our proven path planning and GPS system, in conjunction with a new real-time kinematics correction service, guides the rover during the autonomous mission to within a 1 meter radius of a provided GPS point. While traveling to the GPS points, users are able to see the rover's autonomously generated pure pursuit path through the driver web interface. To navigate to distant Aruco tags and objects, we use an efficient spiral search pattern equipped with accurate computer vision systems to detect both tags and objects in real time, even amongst cluttered environments and rough terrain. Specifically, we use OpenCV to detect Aruco tags from as far as 10 meters away, and we have trained a YOLO V10 model on a dataset of over 4,000 images of bottles and mallets, leading to a high detection rate. During autonomous roving, our obstacle avoidance algorithm reroutes the rover around obstacles detected by the front-mounted stereo camera.
For the science mission, our arm acquires in-situ soil samples for analysis within our science module. Inside, our spectrometer analyzes for light transmission, emission, and scattering. In total, 4 tests will holistically survey for traces of extinct or extant life. First, protein will be detected via Bradford assay. Increased 595 nanometer light absorbance by the Kumasi Brilliant Blue G250 dye indicates dye-protein interfacing. Then, keratin and beta-carotene are detected via Raman spectroscopy. Both forms of organic matter contain identifiable Raman scattering peaks which will be generated by 532 nanometer laser excitation. Lipids will be further detected via Nile red staining. Excited by the same laser, lipid-bound dye will produce distinct fluorescence. Finally, ATP will be detected via luciferin and luciferase assay. The introduction of ATP to the reagent generates bioluminescence.
The wrist camera and arm work together to capture multiple images to create the panorama, which are automatically stitched together and composited with cardinal directions and scaling. Our communication system allows the capture of high-resolution images for scientific analysis while tracking geographical data such as the altitude and location. For stratigraphic profiles, our science team members have been studying geological strata and their significance to any site's natural history to ensure ready knowledge by competition time. To attain at least 5 grams of subsurface soil of interest, we utilize off-the-shelf components integrated into a custom drilling and caching system. The drill system fills the auger with soil until it collects into a cache and is covered by a servo motor and magnetic lid, preserving a soil sample of interest. Out of the hole drilled, we measure subsurface temperature and humidity with a handheld probe. Drilling actuation and data collection are all consolidated on a single custom PCB that minimizes the electrical footprint in the science configuration.
With custom PCBs that manage power distribution, controls, and communications of the arm, drivetrain, and science modules, our electronics help keep the rover compact, lightweight, and functional.
Special thanks to our sponsors, DigiKey, Thorlabs, ODrive, PCBWay, and DF Robot. Hope to see you at YourC 2025.